Hello everyone, my name is Ji Zhao, a master student majoring in International Industrial Design and Engineering at Shanghai Jiao Tong University. I'm excited to present my thesis, a difficulty adaptive cognitive training game designed based on the theta alpha ratio signal. With an aging population and increasingly complex human-computer interactions, the need for effective cognitive training, or CCT, is urgent. However, traditional CCT systems face a core dilemma: difficulty mismatch. They usually use static, linear difficulty adjustment and cannot sense the user's real-time cognitive state. If the task is too easy, it leads to underload mind wandering, making the training ineffective. If it is too hard, it causes overload withdrawal, leading to a breakdown in user compliance. Our solution: introduce neurophysiological signals, specifically EEG, as objective feedback to build a closed-loop adaptive mechanism for dynamic matching. We established the theta alpha ratio as our core physiological indicator. This brings us to our core research question: how can we utilize the TAR signal to build a cognitive training system that accurately perceives an individual's cognitive state and achieve a dynamic closed-loop difficulty adjustment? To answer this, we first conducted a pre-experiment. We designed a parameterized mental arithmetic probe task with 3 difficulty levels: easy, medium, and hard. We recruited 28 participants and collected their EEG data from the occipital region to extract TAR features. The experimental timeline included preparation, a resting baseline, and 3 4-minute task blocks with breaks. We logged real-time EEG data and subjective reports. This pre-experiment led to a crucial discovery: TAR changes non-monotonically with cognitive load, breaking the linear assumption. Look at the trends. In the resting state, TAR is at its lowest baseline. In the easy task, TAR significantly increases as cognitive resources are recruited. In the medium task, TR is maintained at a high level, indicating optimal arousal. However, in the hard task, TR significantly drops. Our key conclusion here is that under extreme overload, the brain triggers a protective inhibition, actively withdrawing resources. Traditional linear model misinterpreted this drop as relaxation, continually increasing difficulty and exacerbating the breakdown. These differences between easy and hard were statistically significant, with a large effect size. Another crucial finding is individual heterogeneity. A universal threshold simply falls. As shown, the absolute TR baseline varies hugely across 28 subjects. For instance, a high baseline user's TARs during overload might still be higher than a low baseline user's peak TAR. Therefore, we developed an individualized calibration mapping framework, including calibration, thresholding, and online mapping. This approach compresses calibration time, avoids the cold start problem, and achieves an optimal AUC of 0.885. We applied this framework to develop a 2D motion system. We used a loosely coupled cross-process architecture, including hardware, algorithm, and front-end. Our key design decisions include a strict artifact rejection mechanism and updating difficulty only during non-operational periods to avoid interpreting cognition. The visual design prioritized a high signal-to-noise ratio and a zero interference principle, while physiological changes implicitly adjust the next round's parameters without breaking immersion. The core of our adaptive algorithm is a 6-state decision matrix that fuse behavior performance with physiological arousal. For example, state 3, good accuracy, high TAR, do a micro increase difficulty to maintain the sweet spot and protect neuroplasticity. State 6, low accuracy, low TAR, then the algorithm will decrease difficulty to prevent compliance breakdown. We also implemented safety logs, capping the number of targets between 1 to 5 to respect human working memory limits. We We evaluated the system efficiency through a formal within-subject crossover experiment with 22 participants, comparing the adaptive mode with a fixed linear mode. The results are compelling. While the average accuracy was identical, the adaptive system advantage lies in its stability. At the same accuracy, the adaptive mode reduced reaction time volatility by 62%. This shows the system effectively stabilized cognitive rhythm during continuous high-load tasks. Physiologically, the adaptive intervention drastically expanded the optimal working zone. The adaptive mode kept the participant in this optimal zone 65.9% of the time, compared to 40.9% in the linear mode. Crucially, the rate of overload withdrawal plummeted from 20.5% down to just 4.5%. These disappearances of physiological and behavior bottling out proves the closed-loop intervention is effective in preventing cognitive overload. Subjectively, the ADAPT system significantly outperformed the linear system in both flow experiences and technology acceptance. Furthermore, the TAR standard deviation for the adaptive system was very low, indicating it effectively eliminated the experience gap caused by inherent individual differences in cognitive ability. In summary, this research validated the non-linear invented U mapping of TAR to cognitive load, established an individualized relative threshold calibration scheme, constructed a 6-stage decision model fusing performance and arousal, delivered a consumer-grade prototype that significantly reduces overload withdrawal and increases the optimal working zone. This completes the methodological loop from theoretical modeling to engineering implementation for neuroadaptive cognitive training. Thank you for your time.